In November 2023, the most distant object ever constructed by human hands began to speak in tongues. Voyager 1, then 15 billion miles from home, started transmitting incomprehensible data. For 5 long months, a dedicated team of only 12 engineers embarked on the monumental task of repairing a computer from across the solar system. The communication delay was staggering. Every command took 22.5 hours to reach the probe, and any response required another 22.5 hours to return. A single diagnostic exchange took almost 2 days to complete, all to debug a machine with less memory than a modern kitchen appliance. Eventually, they isolated the problem to a single, corrupted memory chip. Since a physical replacement was impossible, they devised an ingenious solution. They meticulously broke the affected code into smaller fragments, distributed them across the computer's remaining healthy memory, and then painstakingly rewrote every reference by hand. The gambit worked, but this victory is set against a somber reality. Voyager is nearing the end of its life. Its plutonium power source is decaying, forcing its instruments to be powered down one by one. In November 2026, it is projected to become the first human artifact to be one light day from Earth, a distance so vast that a command sent on a Monday morning would not receive a reply until Wednesday, shortly before the probe is predicted to fall silent forever. This is the story of what that intrepid probe found at the edge of everything we know, and what it found there would fundamentally change our understanding of the cosmic neighborhood we call home. If you appreciate these deep explorations of science and space, your support for Calm Space helps us create more documentaries like this. Before we begin our journey, however, let us consider a different kind of problem, one much closer to home. It is possible your pillow is quietly undermining your health. You may find yourself snoring, waking up exhausted, or experiencing a stiff neck and numb arms. You might even stop breathing momentarily in your sleep. Too often, we dismiss these as normal discomforts of life, but they don't have to be. These symptoms could indicate that your airway is being constricted, your spine is misaligned, or your nerves are being compressed, night after night. The right pillow could make a significant difference. The Derrila Ergo is specifically engineered to maintain an open airway, support proper spinal alignment, and relieve pressure on your nerves. It may be the key to finally waking up feeling genuinely rested. I earn a small commission if you use the link in the description, at no additional cost to you, and a limited offer is available now. It may be worth investigating before the problem worsens. Now, let us begin. Tonight, we are venturing to a place no human has ever gone. Our destination is not the ocean depths or the surface of Mars. We are traveling to the literal edge of our sun's influence, the boundary where our solar system ends and the true void of interstellar space begins. Our guides on this expedition are 2 small spacecraft, launched in 1977 with less computing power than the phone in your pocket. These probes were built for a mission that was supposed to last only 5 years, yet they are still operating nearly half a century later, sending signals back from a region of space no one was sure they would ever reach. This journey will trace the story of the Voyager missions, from the crisis that nearly silenced Voyager 1-inch 2023, to the startling revelation that the solar system extends billions of miles farther than any scientist predicted. We will explore the discovery that the protective bubble enveloping our solar system is not shaped like a comet, as textbooks have shown for decades, but may instead resemble a deflated croissant. We will also investigate evidence suggesting that 2 million years ago, a dense interstellar cloud could have stripped this protective shield away completely. This event would have exposed Earth directly to harsh galactic radiation, raising the question of whether it might have triggered an ice age. Our tour will take us past volcanoes erupting on a moon of Jupiter, beneath the ice of another moon hiding a vast ocean, and through the liquid methane rain of a moon orbiting Saturn. Standing at this cosmic shoreline, we will even listen to the faint, ambient sounds of interstellar space itself. And after witnessing all this, we will be left to ponder a profound question. What does it mean that two tiny machines, built with 1970s technology, have traveled farther than anything in human history, only to teach us that our most fundamental assumptions about the boundaries of our world were wrong? Chapter 1. The spacecraft that would not die. In November 2023, something went profoundly wrong with Voyager 1. The spacecraft, then over 15 billion miles from Earth and moving through interstellar space at 38,000 miles per hour, had been transmitting data reliably for 46 years. Then, one day, that stream of information became incoherent. The flight data subsystem, the onboard computer responsible for packaging all science and engineering data for transmission, began sending gibberish. It was not silence or static. It was a repeating, meaningless pattern of ones and zeros. The telemetry modulation unit, which sends the signal, was working perfectly. The radio was still on. Voyager 1 was still talking, but it had lost the ability to speak a language we could understand. For the engineers at the Jet Propulsion Laboratory in Southern California, this was a nightmare. Voyager 1 is not merely a machine. It is humanity's farthest ambassador and our only direct sensor currently operating in interstellar space. If it were lost, that unique window to the galaxy would close, perhaps for generations. There is no backup mission, no replacement ready to launch. There is simply nothing else out there. The problem was made nearly insurmountable by the immense distance involved. A radio signal, traveling at the speed of light, requires 22.5 hours just to reach the spacecraft. Any response would take another 22.5 hours to return. A single back-and-forth conversation took nearly 2 full days, making troubleshooting an exercise in extreme patience and precision. It was like fixing a complex engine by shouting instructions to someone on the other side of the world and waiting 2 days to see if they worked. The team at JPL is remarkably small, consisting of around a dozen engineers. Some have spent their entire careers working on the Voyager mission, while others are retirees in their ATS who serve as consultants, their knowledge of the vintage hardware being irreplaceable. These were the individuals tasked with debugging a computer from 15 billion miles away, a computer that operates on just 69 kilobytes of memory, a fraction of the data in a single photo from your phone. For months, the team tried everything in their playbook. They toggled instruments on and off. They sent a series of diagnostic commands, each attempt followed by the agonizing multi-day wait for a reply. Nothing worked. The stream of gibberish continued. Then, on March 1st, 2024, they attempted a new tactic. They sent a specific command, a gentle nudge that engineers call a poke, designed to prompt the flight data subsystem to send a complete dump of its memory back to Earth. 2 days later, something new arrived. At first glance, it was more gibberish, but an engineer at the Deep Space Network recognized a faint, underlying structure. It was not random noise. It was the full memory readout they had been hoping for. For weeks, the mission team faced a stream of incomprehensible data. Voyager 1 was sending back the entire contents of its flight data subsystem, but in a raw format that hadn't been used in decades. Engineers meticulously analyzed the readout, comparing it line by line against the last known stable version of the software. Eventually, they isolated the problem. A single memory chip had failed. After 46 years in the harsh environment of space, a tiny piece of silicon had finally given out, possibly due to a cosmic ray strike or simple wear. This failure corrupted 3% of the flight data subsystem's memory, and that small fraction contained the critical code that instructed Voyager on how to format its telemetry for Earth. The spacecraft could still gather information, but it had lost the ability to package it in a way that ground control could understand. Repairing the chip was impossible. There are no service calls in interstellar space. Instead, engineers devised an ingenious workaround. They planned to relocate the corrupted code to other, functional parts of the computer's memory. The challenge, however, was that no single free location was large enough to hold the entire affected block of code. This required an extraordinary feat of remote programming. The team broke the code into smaller fragments, distributed them across various locations in the computer's memory, and then painstakingly rewrote every reference and pointer so the system could locate each piece in its new home. On April 18th, 2024, this patched code was transmitted to Voyager 1. 22.5 hours later, the command arrived. By April 20th, the spacecraft was speaking clearly again, sending readable telemetry. It was the most remote computer repair in human history, performed on hardware older than most of the people who saved it. By June, the probe had resumed transmitting its full science data. But this triumph also brought a sobering truth into sharp focus. Voyager is dying. Its demise won't be sudden or dramatic, but a steady, inevitable decline. Both Voyager probes are powered by radioisotope thermoelectric generators, which convert the heat from decaying plutonium-238 into electricity. When they launched in 1977, each generator produced around 470 watts of power. However, plutonium decays at a fixed rate, and as a result, each spacecraft now loses approximately 4 watts of power every year. This is a relentless calculation that cannot be negotiated. To conserve the dwindling energy, NASA has begun shutting down instruments. In February 2025, Voyager 1's cosmic ray subsystem, a set of 3 telescopes that helped confirm its entry into interstellar space, was powered down. In March 2025, Voyager 2's low-energy charged particle instrument followed. Each spacecraft is now operating with just 3 scientific instruments. As Linda Spilker, the project scientist at JPL, stated plainly, any day could be their last. Yet, that final day could also deliver one more interstellar revelation. Even as its power wanes, Voyager 1 is closing in on one last, remarkable milestone. Around November 15th, 2026, the spacecraft will reach a distance of 16.1 billion miles from our planet. At that point, a radio signal traveling at the speed of light will take precisely 24 hours to reach it. This means a command sent on a Monday morning would not yield a response until Wednesday morning. Voyager 1 is set to become the first human-made object to be one light day away from home. This impending milestone serves as a powerful symbol of the mission's incredible scale. A spacecraft built to last 5 years is now approaching its 50th anniversary. Its computers, designed with only 69 kilobytes of memory, continue to process data from a region of space that no model had predicted they would ever reach. And all the while, the plutonium that gives them life is slowly running out. We are witnessing the end of a legendary era in real time. But before these explorers fall silent, it is worth understanding what they discovered, because their findings at the edge of our solar system transformed our entire conception of our place in the cosmos. For decades, scientists believed they had a firm grasp on where the solar system ended. This boundary wasn't defined by the orbits of the planets, which are merely the system's inner furnishings. The true edge is marked by a far more fundamental transition, the point where the sun's physical influence finally yields to the galaxy. To grasp the significance of Voyager's journey, one must first understand the invisible forces that shape our solar system. Our star is constantly bleeding matter, a continuous stream of charged particles, primarily protons and electrons, that are torn from its outer atmosphere and hurled outward at speeds between 250 and 500 miles per second. This phenomenon is known as the solar wind, and it is immensely powerful. The sun ejects roughly 1 million tons of this material into space every second. This plasma is so intensely hot that its atoms are stripped apart, and it races past all the planets, filling an enormous bubble of space with the sun's own substance. But this solar bubble does not expand into a true vacuum. Filling the vast emptiness between the stars is another medium, a tenuous mixture of hydrogen and helium gas, cosmic rays from distant supernovae, and tangled magnetic fields. This is the interstellar medium. In the Sun's galactic neighborhood, it is incredibly sparse, with only about 1/10 of a particle per cubic centimeter. Despite its thinness, it is ever present, and it pushes back against the Sun's outflow. Far from our star, a point of equilibrium is reached where the outward pressure of the solar wind is perfectly balanced by the inward pressure of the interstellar medium. Here, the solar wind can push no farther. It slows, compresses, heats up, and ultimately halts. This cosmic standoff creates an invisible but critical frontier known as the heliopause, which marks the boundary where the Sun's domain ends and interstellar space begins. The entire bubble inflated by the solar wind is called the heliosphere. Before the Voyager missions, scientific models had offered detailed predictions about where this boundary should lie. Decades of refined magnetohydrodynamic simulations all converged on a similar answer. The heliopause was expected to be located somewhere between 90 and 100 astronomical units from the Sun, a distance of roughly 8 to 9 billion miles. The models also predicted a clear signature for a spacecraft crossing this line. The Sun's magnetic field and the galaxy's magnetic field are oriented in different directions, so there should be a distinct, clean, and measurable rotation in the magnetic field upon crossing over. The problem was, reality refused to cooperate with the prediction. When Voyager 1 reached this predicted zone in the early 2000s, scientists waited for the signal, and they continued to wait. The spacecraft flew onward, past 90 astronomical units, then 95, then 100. The boundary simply wasn't there. Instead of a clean break, Voyager began to register something entirely unexpected, a region scientists would eventually name the magnetic highway. In this zone, magnetic field lines from the inner heliosphere appeared to connect directly with those in interstellar space, forming a kind of bridge between two worlds. This discovery carried profound implications. Particles from inside the solar bubble were seen pouring outward, while particles from the cosmos were simultaneously streaming inward. The boundary was leaking. It was permeable in a way no simulation had ever foreseen. The final crossing, when it occurred, was not a sharp, defined line. It was a gradual, messy, and confusing transition that took years to definitively confirm. The number of cosmic rays detected rose slowly, while the count of solar wind particles diminished at a similar pace. The magnetic field did change, but not in the clean, predictable rotation everyone had anticipated. For over a year, a debate raged in the scientific community. Had Voyager 1 actually left the heliosphere, or was it simply navigating a previously unknown transitional zone? The official NASA announcement did not come until September of 2013. They confirmed Voyager 1 had passed through the heliopause on August 25, 2012, at a distance of 121 astronomical units, not 90, not 100, but 121. That is over 11 billion miles from the Sunday. The edge of our solar system was 2.4 billion miles farther away than every major prediction had calculated. The models were not off by a small margin. They were wrong by a distance greater than that from the Sun to Saturn. A crucial second data point was provided 6 years later by Voyager 2. It crossed the heliopause on November 5, 2018, at a distance of 119 astronomical units, which was 2 astronomical units closer to the Sun than its predecessor's crossing point. Its passage through the boundary was also markedly different. Voyager 2's transition was sharper, faster, and more abrupt. Whereas Voyager 1 had lingered for months within a fuzzy, ambiguous zone, Voyager 2 appeared to punch through in a matter of days. This direct comparison revealed a fundamental truth. The boundary was not uniform. It was lumpy, uneven, and its characteristics varied depending on the location of the crossing. This realization was more than a simple refinement of scientific models. It hinted at a structure far more complex and dynamic than anyone had previously imagined. The nature of the heliosphere is not just an abstract scientific curiosity. It functions as a shield. This massive magnetic bubble is responsible for blocking roughly 75% of galactic cosmic rays from entering the inner solar system. These are not harmless particles. They are atoms, stripped of their electrons and accelerated to nearly the speed of light by the shockwaves from distant supernovas. With the power to damage DNA and disrupt sensitive electronics, they represent one of the most significant hazards of deep space travel. In one respect, the discovery that the heliosphere is larger than previously thought is good news because it suggests we are better protected than the models had indicated. However, this discovery also brings a troubling implication. Our understanding of how this protective shield has changed over the course of history is probably flawed. As it turns out, the heliosphere is not a static entity. It effectively breathes, expanding when the sun is active and contracting when it is quiet. Over millions of years, as our solar system travels through different galactic regions and encounters interstellar clouds of varying densities, the heliosphere's size and shape can change dramatically. If our models for its present-day size were incorrect by 20 to 30%, then our models of its historical dimensions are almost certainly even more unreliable. This uncertainty leads to far-reaching consequences. It means that our estimates for the amount of cosmic radiation Earth has been subjected to over geological time must be revised. It means our calculations for radiation exposure for future astronauts who venture beyond the inner planets need to be updated. And it means that when we evaluate distant star systems for potentially habitable planets, we must now consider the fact that we do not fully grasp the workings of our own protective bubble. The boundary of our solar system was not where we had drawn it on our maps. It was located billions of miles farther out, and it was messier, stranger, and more dynamic than anyone had ever conceived. Yet, even more surprising than its sheer size was the revelation about the bubble's true shape. The heliosphere is not actually a sphere. It does not even resemble the familiar comet-like form that appeared in textbooks for decades. According to research published in 2020, its structure might be something far stranger, a shape that one team of astrophysicists described, with complete seriousness, as a deflated croissant. This peculiar geometry is the subject of our next chapter. For as long as scientists have contemplated the heliosphere, they have attempted to visualize its form. For many decades, that picture remained consistent across every textbook, lecture, and simulation. It was a comet. This model depicted a rounded nose at the front, where the solar system plows through interstellar space, and a long, streaming tail that trailed behind it for hundreds or even thousands of astronomical units. The concept was highly intuitive. One could imagine a boat moving through water, its bow pushing the water aside while a long wake trailed behind. In this analogy, the sun is the boat, the interstellar medium is the water, and the heliosphere is the wake. There was, however, one fundamental problem with this elegant idea. There was almost no data to confirm it. The Voyager probes provided exactly 2 data points on the boundary, just 2 single locations where a spacecraft had physically touched the edge. It is impossible to determine a 3-dimensional shape from only 2 dots. One can guess, model, and simulate, but one cannot truly know. In 2015, a team led by Boston University astrophysicist Merav Ofer published a paper that directly challenged the long-held comet model. By using data from Voyager 1 and new computer simulations that treated the sun's magnetic field as a dominant force, Ofer proposed something radically different. She argued that the heliosphere might not possess a long tail at all. Instead, her models indicated that 2 jet-like structures could be trailing behind the central bulge, curling away from each other, much like the horns of a crescent. The resulting shape, she suggested, was more akin to a croissant than a comet. The response from the scientific community was intense. Ofer later recalled being challenged at nearly every conference she attended, but she stood by her team's findings. Then, in 2020, her team published a landmark paper in Nature Astronomy that introduced new data to support their hypothesis. This time, their argument was bolstered by observations from 3 separate NASA missions: the 2 Voyager spacecraft, the Cassini orbiter at Saturn, and the New Horizons mission flying past Pluto. The key to their analysis was a specific class of particles known as pickup ions. These are atoms from interstellar space that drift into the heliosphere in an electrically neutral state. Since they carry no charge, the sun's magnetic field does not deflect them, and they simply wander in. Once inside, however, they collide with solar wind particles, which strip their electrons away. Now charged, they are picked up by the solar wind and carried along with its flow. It was the behavior of these specific particles that held the critical clue to the heliosphere's true shape. Data from the New Horizons spacecraft revealed a crucial detail regarding these pickup ions. They are incredibly hot, with temperatures hundreds to thousands of times greater than particles of the ordinary solar wind. This finding became the cornerstone of a new model by astrophysicist Mirav Ofer, who proposed treating these 2 populations separately rather than as a single, uniform fluid. When the cold solar wind is computationally isolated from the superheated pickup ions, a remarkable picture emerges. It becomes clear these hot ions are the dominant thermodynamic force in the outer heliosphere, causing the entire structure to puff up into a more spherical, rounded shape. This, however, is only part of the story. Once these pickup ions travel beyond the termination shock, the inner boundary where the solar wind begins to slow, they escape the system at a high rate. As they depart, the internal pressure plummets and the entire structure effectively deflates. The resulting shape is neither a streamlined comet nor a simple sphere. The model instead predicts a deflated, croissant-like bubble, a bulbous central region with 2 chaotic jets twisting away from it, guided by the sun's magnetic field funneling plasma outward. There is no elegant, extended tail, but rather a lumpy, asymmetrical, and constantly shifting shield protecting everything we know. This description might sound almost whimsical, but its implications are profound. The heliosphere is not merely a scientific curiosity. It is a fundamental reason for the existence of life on Earth. Without this protective bubble, our world would be completely vulnerable to the relentless bombardment of galactic cosmic rays. These particles, some of the most energetic in the universe, are accelerated to near light speed by distant supernovas and other violent cosmic events. The heliosphere successfully blocks approximately 75% of these incoming rays, while Earth's own magnetic field and atmosphere manage the remainder. If that primary shield were to vanish, the flux of cosmic rays at the planet's surface would surge, leading to increased radiation exposure, widespread DNA damage, and significant changes to the upper atmosphere that could potentially alter global climate patterns. In 2024, Ofer and her colleagues published research that transformed this hypothetical scenario into a disturbingly plausible event from our planet's past. In collaboration with astrophysicist Avi Loeb of Harvard and astronomer J.G. Peak from the Space Telescope Science Institute, the team traced the sun's journey through the galaxy over the last 2 to 3 million years. Their findings were startling. It appears that approximately 2 million years ago, our solar system passed directly through an unusually dense interstellar cloud. This was not the thin, tenuous medium the sun normally traverses, but a region known as the local links of cold clouds, a patch of gas with a particle density about 3,000 times greater than the typical interstellar environment. To put this into perspective, The Sun usually moves through space with about 1/10 of a particle per cubic centimeter. This cloud, however, contained around 3,000 particles in that same volume. As the solar system plowed into this dense wall of gas, the external pressure exerted on the heliosphere would have been enormous. The team's models indicate this pressure could have compressed the heliosphere from its normal size of over 100 astronomical units down to a mere fraction of that distance. The compression may have been so extreme that the boundary of the heliosphere retreated to a position inside Earth's orbit. If this happened, our planet would have been, for the first time in millions of years, directly exposed to the raw interstellar medium, stripped of its protective shield. This potential exposure meant galactic cosmic rays could have poured in unfiltered. Interstellar hydrogen would have flooded the inner solar system, bringing with it particles that do not originate here, such as radioactive isotopes forged in the hearts of dying stars. What makes this research so compelling is the timing. The period 2 to 3 million years ago coincides precisely with the beginning of the series of ice ages, known as the Quaternary glaciation. It also aligns with documented spikes of iron, 6-0, and plutonium-244 found in deep-sea sediment cores and Antarctic snow. These isotopes are not produced naturally on Earth or within our solar system. Their origin is interstellar, from supernova explosions. The fact that they appear in our geological record at the exact moment the heliosphere may have collapsed presents a powerful question. Is this a remarkable coincidence, or is it evidence that the collapse truly occurred? Did the influx of galactic cosmic rays alter Earth's atmosphere, perhaps by increasing cloud formation, which would reflect more sunlight and cool the planet? While the research does not prove causation, it does establish a credible physical mechanism. It demonstrates that the edge of our solar system is not an abstract, static line, but a dynamic and variable boundary, one that breathes, shifts, and can occasionally fail. And when it fails, Earth feels the consequences. This very possibility is why understanding the heliosphere is so critical, and why NASA has launched a mission specifically to map this invisible frontier. On September 24, 2025, the Interstellar Mapping and Acceleration Probe, or IMAP, launched from Cape Canaveral. By February 1st, 2026, it had settled into its operational orbit at the L1 Lagrange point, a stable position about 1 million miles from Earth, directly between our planet and the Sunday. IMAP is equipped with 10 scientific instruments, one of which is designed to capture interstellar dust particles as they drift through our solar system. Its primary instrument, however, uses a technique detecting energetic neutral atoms, or ENAs, as a form of radar. These particles originate in the turbulent outer region of the heliosphere and fly back toward the Sun without being deflected by magnetic field. By analyzing the direction, energy, and quantity of these returning atoms, IMAP can construct a map of the heliosphere's boundary from within, much like using sonar to map the walls of a cave. The mission's goals are to provide definitive answers to long-standing questions. IMAP will test if the heliosphere is truly croissant-shaped. It will measure how the boundary responds to the Sun's changing activity and track how cosmic rays manage to penetrate our defenses, identifying the shield's weak points. For the first time, this mission will give us a dynamic, detailed, and continuously updated picture of the very structure that protects all known life. We have spent our entire history inside this bubble, unaware of its existence until the space age. We did not touch its edge until the Voyager probes. Only now are we beginning to comprehend its true shape and realize this invisible boundary may have directly influenced the course of life on Earth. But to fully appreciate what Voyager found, we must return to its beginning to 1977, to a rare planetary alignment, and to the bold decision to send 2 spacecraft farther than anything had gone before. Chapter 4, 1977, and the Grand Tour. In the late 1960s, a young aerospace engineer at the Jet Propulsion Laboratory named Gary Flandreau, was performing what might have seemed like routine calculations. While studying potential trajectories for missions to the outer planets, he uncovered something truly remarkable. Flandreau realized that in the late 1970s, the four gas giants Jupiter, Saturn, Uranus, and Neptune would fall into a rare alignment, a celestial configuration that occurs only once every 176 years. This specific arrangement meant a single probe could visit all four of these worlds in a single continuous journey by using a series of gravitational assists. This slingshot maneuver is a masterpiece of orbital mechanics. As a spacecraft approaches a planet on a precise path, the planet's immense gravity captures it, pulling it in and accelerating it. The probe then swings around the planet and is catapulted back out into space, now traveling at a significantly higher speed. It essentially borrows a tiny, imperceptible amount of energy from the planet's own orbit. For the massive planet, the exchange is negligible. For the tiny spacecraft, it is a game changer, providing a powerful boost in speed and a change in direction without consuming any fuel. By chaining these assists together, a craft could leap from Jupiter to Saturn, then to Uranus, and finally to Neptune, completing a tour of the outer solar system in roughly 12 years. A direct flight would have taken 30 years or more. This raises a profound question. How much of scientific discovery is not just brilliance, but also being in the right place at the right time? With the next alignment not due until the year 2153, the window of opportunity was fleeting, and for the generation of scientists alive then, it was now or never. NASA's initial concept, known as the Grand Tour, was as ambitious as the opportunity itself, envisioning a pair of spacecraft to visit all four of the outer planets. However, grand visions often collide with earthly realities. In the early 1970s, severe budget cuts forced the agency to retreat from this plan. The mission was subsequently redesigned and scaled down into the Mariner Jupiter-Saturn project, a more modest proposal to send two spacecraft only as far as Jupiter and Saturn. This 5-year mission was simpler, more affordable, and therefore more politically acceptable. But the engineers behind the project harbored a quiet hope for something more. They designed the spacecraft with a level of durability and redundancy that far exceeded the requirements of a 5-year mission. This foresight, building in flexibility and resilience that would prove indispensable decades later, was a silent testament to their belief in the probe's potential for a much longer journey. Eventually, the project was given a new, more evocative name, Voyager. The launch sequence was a carefully choreographed dance of orbital mechanics. Voyager 2 was the first to leave Earth, lifting off on August 20th, 1977. Just 16 days later, on September 5th, Voyager 1 followed. Despite its later departure, Voyager 1 was set on a faster, more direct trajectory. This meant it would overtake its sibling and be the first to arrive at Jupiter. The naming of the probes thus reflects the planned order of their planetary encounters, not the order in which they left our world, a small detail that highlights the intricate planning involved from the very beginning. The technology aboard the Voyager probes was at the cutting edge for its era, yet by modern standards, it appears almost impossibly primitive. This contrast underscores the sheer ingenuity of the mission. Each spacecraft was equipped with 3 custom-built computers from General Electric, which together offered a total memory of just 68 kilobytes, not megabytes or gigabytes. A typical smartphone today possesses over 1 million times that capacity. For data storage, the probes relied on an 8-track digital tape recorder capable of holding about 536 megabits, or roughly 67 megabytes. That is less than the file size of a single high-resolution photograph taken with a modern camera. The radio transmitter, humanity's only link to these distant emissaries, broadcast its signal with a mere 23 watts of power, which is less than the bulb illuminating the inside of a refrigerator. That faint 2-3 watt signal, traveling across billions of kilometers, presents an extraordinary challenge for communication. By the time it reaches Earth from the depths of interstellar space, it has weakened and spread out over such a vast area that the power collected by our largest antennas is an almost infinitesimal 1/quintillionth of a watt. It remains the faintest signal that humanity consistently detects and decodes. To capture this whisper from the void, NASA depends on its deep space network, a global system of 3 massive antenna complexes, located near Barstow, California, Madrid, Spain, and Canberra, Australia. Their placement ensures that as the Earth rotates, at least one station always has a direct line of sight to any given spacecraft. The largest of these radio dishes measure 230 feet across and are among the most sensitive receivers ever constructed. Without this incredible infrastructure, the Voyager probes would be shouting into an empty abyss, their historic journey unheard. Powering a mission into the dark outer reaches of the solar system required a solution far beyond conventional technology. Solar panels become ineffective past the orbit of Mars, where the sun is too distant and dim to provide sufficient energy. Consequently, each Voyager spacecraft was equipped with 3 radioisotope thermoelectric generators, or RTGs. These remarkable devices contain pellets of plutonium-238, a radioactive isotope that naturally generates a steady supply of heat as it undergoes atomic decay. This heat is then converted directly into electricity by a set of thermocouples. The design is elegant in its simplicity, with no moving parts, pumps, or turbines, just the quiet, reliable, and inevitable process of physics transforming matter into power. It is a testament to engineering that such a stable power source could be designed for a journey of unknown duration. At the time of launch, the 3 RTGs on each Voyager probe generated approximately 470 watts of electrical power, but the plutonium-238 that fuels them has a half-life of 87.7 years, meaning the power output is constantly, predictably diminishing. Every year, the available electricity drops by about 4 watts. This is not a system failure or a malfunction. It is an immutable law of physics. The decay of the plutonium cannot be stopped, reversed, or even slowed. It proceeds at its own unyielding pace, regardless of any human intervention. Now, after nearly half a century in space, the power budget for each Voyager has fallen below 200 watts and continues its slow decline. This steady depletion of energy is the true ticking clock of the Voyager mission, not the threat of a mechanical breakdown or a software glitch, but the quiet, relentless decay of the very atoms that keep its systems alive. This dwindling power supply has forced mission engineers into a delicate, long-distance balancing act. They are essentially performing triage on hardware that was constructed before many of them were even born. Every instrument that is permanently shut down buys a few more precious months of life for those that remain operational. Every clever engineering trick that manages to save a watt or two extends the mission's reach just a little farther into the unknown cosmos. But there is an element to the Voyager spacecraft that elevates them beyond their technical specifications, something that distinguishes them from every other mission NASA has ever launched. This is the story of their cultural, not just scientific, cargo. Bolted to the side of each Voyager probe is a golden-plated copper phonograph record, protected by an aluminum cover, the Golden Record. It was the brainchild of Carl Sagan, the celebrated astronomer and science communicator, who led the committee responsible for selecting its contents. The record was conceived as a message in a bottle, a greeting to any civilization that might one day encounter the spacecraft. The record is a time capsule of Earth in the 1970s. It carries 116 images, encoded as audio waveforms, depicting scenes of science, nature, and human life. It also contains spoken greetings in 55 different languages, from ancient Akkadian to modern Mandarin Chinese. A curated selection of 27 musical pieces represents a global tapestry of sound, including works by Johann Sebastian Bach and Chuck Berry, alongside a Japanese shakuhachi performance and songs from Aboriginal Australians. Finally, it includes The Sounds of Earth, a collection of audio clips featuring a baby's cry, the sound of a kiss, the roar of wind and rain, the calls of humpback whales, and the thunderous ignition of a Saturn V rocket. It is a portrait of our world, defined by its sounds and images. To ensure this message could be understood, the record's cover is etched with a set of instructions. It includes a diagram showing how to play the record and a pulsar map designed to serve as a cosmic address. This map pinpoints the location of our Sun relative to 14 known pulsars, each identifiable by its unique rotational period, acting like a celestial fingerprint. The map also cleverly encodes the time the record was created, using the predictable decay of hydrogen as a universal clock. Every aspect of its design speaks to a hope for longevity, a desire to create a message that could survive for 1 billion years, raising the ultimate question of whether anyone will ever be there to receive it. In the vacuum of space, gold is eternal. It does not corrode. On the Voyager golden record, there are no electronics that can degrade over time, no magnetic media that can lose its charge across the eons. The information is etched directly into the material, meaning the grooves containing humanity's story will remain readable for hundreds of millions of years. And yet, for all its permanence, the probability that either record is ever found by another intelligence is practically zero. Space is simply too vast, and the spacecraft are too small, too cold, and too dark to be easily detected. They are not even aimed at a specific star. In 40,000 years, Voyager 1 will pass within 1.6 light-years of a star named Gliese, 445. But this is still a cosmic near-miss, not a true rendezvous. This raises a crucial question. If the record was never truly meant to be found, what was its purpose? The golden record was not a serious attempt at interstellar communication. Instead, it was an act of profound self-reflection. It was a moment when a species, in the midst of a complex engineering project, paused to ask fundamental questions. Who are we? What defines us? What is worth preserving for eternity? The answer, inscribed in gold and sent into the void, is still traveling at over 38,000 miles per hour. This artifact will outlast the pyramids, the continents, and perhaps even the sun itself. But before the Voyager probes could reach for the stars, they first had to navigate the most spectacular neighborhood in our solar system, the realm of the giant planets. What they uncovered there was as astonishing as anything they might later find at the edge of the sun's influence. Chapter 5: Fire and Ice, Jupiter and its Moons. Voyager 1 arrived in the Jovian system in March of 1979, followed by Voyager 2 a few months later in July. The data they transmitted back to Earth didn't just add to our knowledge. It rewrote the textbooks on planetary science almost overnight. The planet Jupiter itself was revealed to be more violent, more intricate, and more beautiful than anyone had ever conceived. Yet the most profound shocks came not from the gas giant, but from its collection of moons. Our understanding of the solar system was about to be permanently altered. Prior to the Voyager mission, our view of Jupiter was limited to telescopic observations and a handful of blurry images from the Pioneer 10 and 11 flybys in 1973 and 1974. We understood the basics, that Jupiter was a gas giant. Its atmosphere was marked by colorful bands of clouds, and it was home to the Great Red Spot, a storm observed for centuries. What we lacked, however, was any real sense of what these features looked like up close. The reality, as it turned out, was far more dynamic than our distant observations had ever suggested. Voyager's cameras revealed Jupiter's atmosphere to be a churning, turbulent engine of staggering complexity. The familiar cloud bands were not smooth, uniform layers at all. They were twisted with countless eddies, vortices, and smaller storms caught within the larger atmospheric flow. Enormous bolts of lightning, which released up to 1,000 times more energy than the most powerful strikes on Earth, crackled through the deep clouds. At the poles, auroras blazed 1,000 times brighter than our own, powered by the interplay between Jupiter's immense magnetic field and charged particles spewing from its volcanic moon, Io. The Great Red Spot, observed in detail for the first time, was identified as a colossal high-pressure anticyclone, with its top rising about 5 miles above the surrounding cloud decks. This single storm is wider than the entire planet Earth and has been raging for at least 350 years, with winds at its periphery exceeding 400 miles per hour. In addition to these atmospheric wonders, Voyager made another key discovery: a faint, tenuous ring system around Jupiter. This was the first indication that planetary rings might be a common feature of giant planets and not a unique characteristic of Saturn. But for all the revelations about the planet itself, the true revolution in our understanding began with its moons. It started with Linda Morabito, a navigation engineer whose job was to use images of Jupiter's moons to pinpoint Voyager 1's exact location against the backdrop of distant stars. On March 9th, 1979, she was analyzing an image of Io, the innermost of Jupiter's 4 large Galilean moons. To make the background stars visible for navigation, the image had been deliberately overexposed. As Morabito examined the limb of the moon, its bright crescent edge, she noticed something that simply should not have been there: a vast, umbrella-shaped plume rising from the surface and erupting into space. In that moment, she had discovered the first active volcano ever observed beyond Earth. This plume was enormous, soaring to an altitude of roughly 200 miles above Io's surface. It was a fountain of sulfur and sulfur dioxide, erupting with such force that it was launching material completely off the moon. Subsequent images revealed that this was not an isolated event. Io was covered in erupting volcanoes. The moon turned out to be the most volcanically active body in the entire solar system, with over 400 identified volcanic centers. The eruptions are so frequent and widespread that they completely resurface the moon approximately every million years. This constant geological renewal explains why Io has virtually no impact craters. They are buried under fresh lava flows long before they can accumulate. This discovery presented a major scientific puzzle. Io is a small moon, roughly the size of our own. According to the principles of planetary science at the time, small bodies lose their internal heat quickly, their interiors solidify, and they become geologically dead. Earth's moon is a prime example, as is Mars, for the most part. So why was this small moon erupting with a violence that dwarfed anything on Earth? What could possibly be powering this internal furnace? Remarkably, the answer had been predicted just days before Voyager 1's arrival. In a paper published in the journal Science, 3 scientists, Stanton Peele, Patrick Casson, and Ray Reynolds, proposed that Io was being heated by tidal forces. They theorized that while Jupiter's gravity pulls on Io, so do the other large moons, Europa and Ganymede. Io is caught in an orbital resonance with these neighbors, a gravitational lockstep that constantly pushes and pulls its orbit into a slightly elliptical shape. As Io moves closer to and then farther from Jupiter, the giant planet's immense gravity flexes the moon's interior, much like someone repeatedly squeezing a rubber ball. This constant flexing generates friction, and that friction generates an enormous amount of heat enough to melt rock on a planetary scale. Their paper was published on March 2nd, 1979. Linda Morabito discovered the volcanic plume on March 9th. The theory was confirmed by direct observation within a single week of its publication, representing one of the most stunning instances of prediction meeting discovery in the entire history of science. The significance of this finding extended far beyond Io. Tidal heating introduced a completely new source of geological energy into our models of the cosmos. Before this, the only known mechanism for keeping a planetary body geologically active was the slow decay of radioactive elements in its core. This meant that larger bodies, which contained more radioactive material, stayed warm longer, while smaller bodies cooled and died. Tidal heating shattered that framework. It meant that even a small moon, orbiting far from the Sun in the frozen outer solar system, could possess a hot, active interior. It could have liquid water. In theory, it could even support life. This realization brings us to Europa, the second of the 4 Galilean moons and slightly smaller than Earth's moon. In Voyager's images, Europa looked like nothing anyone had ever seen before. Its surface was almost perfectly smooth, lacking the mountains, valleys, and heavy cratering seen on almost every other solid body in the solar system. Instead, it was crisscrossed by a complex web of dark, linear streaks, some stretching for thousands of miles. It looked less like a rocky moon and more like a cracked eggshell or a frozen ocean. This appearance, combined with the newfound potential of tidal heating, led scientists to a breathtaking hypothesis that beneath its icy crust, Europa might harbor a global ocean of liquid water. The dark streaks were likely cracks in the ice, caused by the same tidal stresses that heat Io, through which darker, salt-rich water from the ocean below had welled up and frozen. The implications were staggering. On Earth, wherever we find liquid water, we find life. If Europa had a liquid water ocean, warmed by tidal forces and potentially supplied with chemical nutrients from its rocky seafloor, it would possess all the necessary ingredients for life as we know it. The Voyager flybys didn't just discover new worlds, they discovered new times of worlds, places where the conditions for life could exist in environments previously thought to be hopelessly barren and frozen. The search for extraterrestrial life suddenly had a new and compelling target. Not on a distant, Earth-like planet orbiting another star, but right here, in our own solar system, orbiting Jupiter. The 2 Voyager spacecraft, having fundamentally and permanently altered our view of the solar system, continued their journey outward, their cameras turning toward their next target, the majestic, ringed world of Saturn. In stark contrast to the familiar, crater-battered landscapes of most moons, Europa presented a startlingly different face. Its surface was a smooth shell of water ice, but it was fractured by a vast network of dark, reddish lines. These features were identified as enormous cracks in the ice, fissures that had been filled with material welling up from the interior before freezing shut again. The near-total absence of impact craters was a profound clue. It meant Europa's surface was geologically young. Some ongoing process was constantly resurfacing the moon, erasing impact scars before they could accumulate over eons. The single most compelling explanation for this activity was the existence of a global ocean of liquid water hidden beneath the ice shell. This subterranean sea would be kept warm not by the distant sun, but by the very same tidal heating mechanism that fuels the volcanoes on its sibling moon, Io. The forces at play on Europa would be less intense, not enough to melt rock, but perhaps just right to maintain liquid water. The Voyager spacecraft could not definitively confirm this hypothesis. Its cameras lacked the necessary sensitivity. Its flyby was far too brief, and its instruments were simply not designed for such a deep investigation. And yet, the hints it gathered were unmistakable and powerful. Those tantalizing clues would go on to launch one of the most ambitious scientific quests of the modern era. In October of 2024, NASA launched the Europa Clipper, a spacecraft born directly from Voyager's legacy. Scheduled to arrive at Jupiter around 2030, its primary mission is to perform dozens of close flybys of Europa, using sophisticated ice-penetrating radar, magnetometers, and spectrometers. It will seek to determine once and for all if an ocean exists and, more importantly, whether that ocean might harbor the conditions necessary for life. Europa Clipper is a direct descendant of the Voyager program, its existence a testament to a chain of discovery. It was made possible because Linda Morabito noticed something on an overexposed image in 1979 that shouldn't have been there, because a paper on tidal heating was published just a week before it was visually confirmed, and because Voyager's cameras revealed a smooth, cracked, and impossibly young surface on a moon that should have been cold and dead. The discovery of tidal heating and its profound implications for habitability is arguably the single most important finding of the entire Voyager mission. It fundamentally changed the equation for where life might exist in the cosmos. Before Voyager, the concept of a habitable zone was defined almost exclusively by a planet's distance from its star, a narrow band where it was close enough for water to be liquid, but far enough to prevent it from boiling away. After Voyager, that definition expanded enormously. The mission revealed that any moon orbiting any giant planet, anywhere in the galaxy, could potentially harbor liquid water if the tidal forces were just right. This powerful realization didn't just increase the number of potentially habitable worlds in the Milky Way, it multiplied them by orders of magnitude, opening up a vast new frontier in the search for life. Jupiter had been the stunning opening act, but the grand tour was far from over. Saturn, with its magnificent rings and enigmatic moons, was next. And beyond Saturn lay the ice giants, Uranus and Neptune worlds that only Voyager 2 would ever visit, and which humanity has seen up close on only that one single occasion. Voyager 1 reached the Saturn system in November of 1980, with Voyager 2 following in August of 1981. If the discoveries at Jupiter had been a revelation, then Saturn was a pure spectacle. Through telescopes on Earth, Saturn's rings appear as a few broad, flat bands of light. Voyager's cameras, however, revealed their true, intricate nature. Each visible ring was, in fact, composed of thousands of individual ringlets, all nested within each other, like the grooves on a vinyl record. Each of these ringlets is a stream of countless particles of ice and rock, their sizes ranging from tiny grains of dust to chunks as large as a house. This entire system orbits Saturn in a disk, stretching hundreds of thousands of miles across space. Yet in most places, it is only about 30 feet thick. The sheer thinness of this structure is almost impossible to fully comprehend. To offer a sense of scale, if you were to shrink Saturn's rings down to the width of a football field, their thickness would be equivalent to a single sheet of tissue paper. Within this impossibly thin and beautiful disk, Voyager discovered a surprising amount of structure and dynamic activity. It saw spokes, which are dark, radial features that appeared to rotate with the planet's magnetic field rather than obeying standard orbital mechanics. It found braids, areas where individual ringlets seemed to weave around one another in defiance of simple gravitational physics. And it observed density waves, which are ripples that propagate through the ring material, much like sound waves travel through air, generated by the gravitational pull of Saturn's many moons. Two small moons, in particular, captured the attention of scientists, Prometheus and Pandora. Orbiting just inside and just outside the narrow F-ring, they were found to be acting as gravitational shepherds. Their combined gravity confines the ring particles into a tight, well-defined band, preventing them from spreading out. This process had been theorized but never directly observed, and its confirmation had implications reaching far beyond Saturn. The same fundamental physics, the gravitational confinement of a debris disk by embedded objects, is at play in the protoplanetary disks around young stars and in the accretion disks surrounding black holes. Saturn's rings were not just a celestial wonder, they were a natural laboratory for understanding how matter organizes itself under gravity across the universe. But for all the wonders of the rings, the most significant discovery at Saturn may have been one of its moons. Titan. As Saturn's largest moon, Titan is bigger than the planet Mercury, and even before Voyager's arrival, it was one of the most intriguing bodies in the solar system. Ground-based observations had already detected an atmosphere, making Titan the only moon known to possess a substantial one. However, no one knew how thick that atmosphere was, or what the surface looked like beneath its perpetual orange haze. Voyager's measurements were astonishing. Titan's atmosphere was not merely present, it was far thicker and denser than Earth's. The surface pressure on Titan is about 1.5 times the pressure at sea level on our own planet. Its composition is 95% nitrogen, much like our air, but the remaining 5% is mostly methane, and that small difference changes everything. On Titan, methane plays the same role that water plays on Earth. At the moon's frigid surface temperature of -290 degrees Fahrenheit, methane exists as a liquid. It evaporates from lakes and seas on the surface, rises into the atmosphere, condenses to form clouds, and then falls as rain. This methane rain collects into rivers and streams, which carve channels into the landscape as they flow back into the lakes and seas. Titan has a complete weather cycle, a hydrological system just like Earth's, but one based on liquid hydrocarbons instead of water. This creates a world that is both strangely alien and hauntingly familiar. Voyager's cameras could not see through the thick haze to the surface below, showing only an opaque, featureless orange ball. But the data it collected about the atmosphere's composition and temperature profile was so compelling that it drove decades of follow-up investigation. That investigation culminated with NASA's Cassini spacecraft, which arrived at Saturn in 2004. Cassini carried a European probe called Huygens, designed to do what Voyager could not, descend to Titan's surface. On January 14, 2005, Huygens plunged through the moon's dense atmosphere, landing safely and transmitting images of a truly alien landscape. The probe revealed a surface littered with dark, rounded pebbles made not of rock, but of hard water ice, resting upon a bed of hydrocarbon silt. It was the farthest landing from Earth ever accomplished by humanity. And even with these incredible achievements, the exploration of Titan is not over, as this strange world continues to beckon with its many remaining mysteries. High in the orange-tinted haze of Titan's atmosphere, a remarkable chemical factory is constantly at work. Here, ultraviolet radiation from the sun forges complex organic molecules called tholins from chains of carbon, hydrogen, and nitrogen atoms. This process is profoundly significant, as these compounds are thought to be remarkably similar to those present on early Earth before life ever arose. Titan, in essence, provides a frozen snapshot of the prebiotic chemistry that may have preceded biology on our own planet. This tantalizing possibility is the driving force behind NASA's Dragonfly mission, scheduled to launch in 2028 and arrive in the mid-2030s. This car-sized, nuclear-powered drone will use its 8 rotors to fly from one site to another across Titan's surface. It will sample the environment, measure its composition, and search for the building blocks of life in a world that has been running a planetary-scale chemistry experiment for billions of years. In its ambitious goals, Dragonfly is a direct intellectual descendant of the Voyager program, continuing a legacy of deep space exploration. After their encounter with Saturn, the 2 Voyager spacecraft embarked on separate paths. Voyager 1's flyby of Titan necessitated a specific trajectory, one that flung the probe upward and out of the plane where the planets orbit. For Voyager 1, the grand tour of the solar system was complete. It set a new course toward interstellar space, destined to make the discoveries we will explore later. Meanwhile, Voyager 2 journeyed on alone. It reached Uranus in January of 1986, and then Neptune in August of 1989. To this day, it remains the only probe ever to have visited either of these distant ice giants, leaving us with our only close-up views of these mysterious worlds. The visit to Uranus revealed a world of profound strangeness. The planet is tilted on its axis by an astonishing 98 degrees, causing it to roll along its orbit like a ball instead of spinning like a conventional top. This extreme orientation strongly suggests that a colossal object must have collided with Uranus early in its history, knocking it onto its side. Its moons were no less peculiar. Miranda, the smallest of the 5 main satellites, appeared as if it had been shattered and then haphazardly pieced back together. Its surface is a chaotic patchwork of starkly different terrains, where smooth plains lie adjacent to grooved regions and ridged canyons. These canyons feature cliffs that tower 6 miles high, among the tallest in the solar system. One leading hypothesis proposes that Miranda was literally broken apart by an ancient impact, only to be gravitationally reassembled with its interior shuffled like a deck of cards. Neptune served as the grand finale of the planetary tour, and it proved to be the most dynamic world Voyager had yet encountered. Despite its vast distance from the Sun, where it receives barely 1/1000th of the solar energy that reaches Earth, Neptune's atmosphere was a scene of violent motion. A massive storm, the Great Dark Spot, swirled in its southern hemisphere, reminiscent of Jupiter's iconic Great Red Spot. Winds on Neptune were measured at over 1,300 miles per hour, the fastest ever recorded on any planet. The source of this immense energy, so far from the Sun, remains one of the great unsolved puzzles of planetary science. The planet radiates more than double the heat it absorbs from the Sun, generated by internal processes that are still not fully understood. Neptune's largest moon, Triton, delivered one final, stunning surprise. Triton orbits Neptune in the wrong direction, moving in a retrograde path opposite to the planet's rotation. This orbital behavior is a near-certain indicator that Triton was not formed alongside Neptune, but was instead a captured object. It was likely a wanderer from the Kuiper Belt, the frozen outer frontier of the solar system that was ensnared by Neptune's gravity and pulled into orbit. On this frigid world, nearly 3 billion miles from the Sun, with surface temperatures around -391 degrees Fahrenheit, Voyager still detected activity. Nitrogen geysers were seen erupting from beneath the icy crust, shooting dark plumes of material 5 miles into Triton's thin atmosphere. These eruptions left long, dark streaks on the surface, carried downwind, revealing geological processes on a world that by all logic should have been completely inert. Following the Neptune encounter, Voyager 2's camera was powered down. There were no more worlds left to photograph. Ahead lay only the vast emptiness of space. The 2 spacecraft, now both pointed away from the Sun, commenced their long journey toward the edge of the heliosphere. This was a destination they were never designed to reach, and its boundary would turn out to be nothing like anyone had predicted. The planetary flybys, the mission the Voyagers were built for, spanned 12 years and yielded more discoveries than any robotic mission before or since. But it was the mission they were not built for the exploration of the frontier between our solar system and interstellar space that would ultimately make them immortal. The first indication that this boundary would defy all expectations came not at the heliopause itself, but billions of miles before it, at a structure known as the termination shock, a place where the Sun's powerful wind finally begins to lose its momentum. Chapter 7. The Termination Shock. To grasp what Voyager discovered at this frontier, it is essential to understand the nature of the solar wind as it travels outward. The Sun does not simply emit particles into space at a steady rate. Instead, the solar wind is a supersonic phenomenon. This is not a metaphor. The particles streaming from the Sun are moving 5 to 10 times faster than the speed of sound within plasma. Sound in plasma, a gas of charged particles interwoven with magnetic fields, travels much more rapidly than in ordinary air. For the solar wind to be supersonic in this medium means it is moving at an exceptionally high velocity. Far from the Sun, However, this powerful wind eventually encounters resistance from the interstellar medium that fills the space between stars. When a supersonic flow meets such an obstacle, it does not slow down gradually. Instead, it creates a shock wave, a sudden and violent deceleration where the flow transitions from supersonic to subsonic over a very short distance. In this process, the plasma becomes compressed, heated, and turbulent, while its density increases by a factor of 3 or 4. This boundary is the termination shock, and its detection was a primary objective for scientists tracking Voyager's journey. Scientific models had predicted that the termination shock would be located somewhere between 75 and 90 astronomical units from the Sun. The first sign that Voyager was approaching it came in August of 2002. At a distance of about 85 astronomical units, Voyager 1 detected a rise in particle intensity, suggesting the shock was close. But then, something entirely unexpected occurred. The shock itself began to move. The termination shock is not a static, impenetrable wall. It is a dynamic, living boundary that shifts in response to the Sun's own activity. When the Sun has a burst of energy, such as a coronal mass ejection or a surge in solar wind pressure, the shock wave is pushed further out into space. Conversely, when the Sun is quiet, the pressure from the interstellar medium pushes the shock back inward. In a sense, the boundary breathes. Voyager 1 witnessed this behavior firsthand. The shockwave seemed to wash over the spacecraft, then retreat, only to advance and recede again. Its instruments recorded the boundary oscillating back and forth, much like the surface of a lake buffeted by a storm. The spacecraft had reached the edge, but it was an edge that refused to stand still. On December 16, 2004, Voyager 1 finally crossed the termination shock at a distance of 94 astronomical units from the Sunday. This was farther out than any model had predicted, an early sign that our understanding was incomplete. But the crossing itself was not a singular, dramatic event. Instead of a clean line, the spacecraft experienced a messy, fluctuating transition that stretched across several astronomical units. The solar wind didn't just stop, its velocity decreased gradually as its fundamental properties changed. This discovery was compounded when Voyager 2 made its own crossing on August 30th, 2007. It encountered the shock at just 84 astronomical units, a full 10 AU closer to the Sun than its sibling craft. This discrepancy offered the first concrete proof that the heliosphere is not a perfect sphere. It is distorted, compressed on the side facing the interstellar medium as our solar system journeys through the galaxy, and elongated in its trailing wake. That 10 AU difference, equivalent to nearly 930 million miles, revealed a dynamic and lopsided structure, fundamentally reshaping our view of the Sun's domain. Beyond this turbulent boundary lies a region known as the heliosheath. Scientists had theorized this would be a relatively predictable transition zone, perhaps 10 to 20 astronomical units thick. In this area, the now subsonic solar wind was expected to slowly lose its energy, mix with interstellar particles, and finally dissipate at the heliopause, the ultimate edge of the Sun's influence. The reality, however, was far from straightforward. The first anomaly involved cosmic rays. Models predicted a steady, gradual increase in cosmic ray detections as the probes moved outward. What Voyager recorded was entirely different. The counts rose in erratic patterns, marked by unexpected plateaus and abrupt spikes. This suggested the particles weren't simply diffusing inward but were being actively guided and funneled by complex magnetic structures no theory had accounted for. Adding to the puzzle was the behavior of the solar wind itself. It began to fade out much earlier than anticipated. Years before Voyager 1 even reached the heliopause, instruments showed solar particle counts dropping in a way that hinted the boundary ahead was not a solid wall, but was perhaps already starting to fray and dissolve. But the most bewildering discovery was yet to come. In the months leading up to its official exit from the solar system, Voyager 1 entered a bizarre region that scientists dubbed the Magnetic Highway. Here, the magnetic field lines seemed to form organized conduits, directly connecting the heliosheath with interstellar space. These channels acted like corridors running perpendicular to the boundary. Along these pathways, particles from within the heliosphere could stream out into the galaxy, while interstellar particles could flow inward. This observation shattered the long-held image of the heliopause as an impenetrable wall. It was, in fact, permeable, featuring distinct lanes for traffic. No model had ever predicted such a feature. It was a discovery only possible through direct measurement. This revealed a boundary that was far more interactive and alive than anyone had imagined. The heliosphere and the interstellar medium weren't just two forces pushing against one another. They were actively exchanging material in a complex, ongoing dialogue. The journey had been a cascade of revelations. The termination shock was a surprise. The heliosheath proved to be a maze, and the heliopause itself was no exception. When Voyager 1 finally crossed it in 2012, the event was not the clean break depicted in textbooks. It was a messy, gradual transition that was so ambiguous it took scientists more than a year to definitively confirm the crossing had even occurred. In some fundamental way, every prediction had been incorrect. Not wildly or absurdly wrong, but consistently too simple, underestimating the sheer complexity of the environment at the edge of our solar system. This may be the most profound lesson from the entire Voyager mission. Our scientific models are powerful tools, built upon solid physics and refined by decades of observation. Yet they are, by their nature, simplifications. When we finally venture out to measure reality directly, it is invariably stranger, messier, and more wonderfully intricate than our theories suggest. This has been a recurring theme throughout the history of scientific exploration, and it proved true once again at the frontier of the sun's influence. Yet the surprises were not over once Voyager 1 crossed into interstellar space. The probe began to detect something entirely unforeseen: shockwaves. These were waves of compressed plasma, rippling through the void between the stars that had been launched by solar events years earlier. This discovery demonstrated that the sun's influence did not abruptly end at the heliopause. It echoed far out into the galaxy. In turn, the galaxy was pushing back in ways that were just as unexpected. This leads us to the next chapter of Voyager's journey: the discovery of tsunami waves and galactic weather in the space between the stars. Upon entering this new realm in August of 2012, the scientific community anticipated that the interstellar medium would be a place of profound quiet. It was expected to be a vast, featureless expanse of thin gas and faint magnetic fields. After the noisy, dynamic environment of the heliosphere, interstellar space was supposed to be the calm beyond the city limits. But again, that assumption was about to be proven wrong. Just 2 months after its historic crossing, in October of 2012, Voyager 1 detected something moving through the interstellar plasma. It was a compression wave, a region of increased density and pressure propagating through the medium much like a ripple on a pond. One of the spacecraft's few remaining active instruments, the plasma wave subsystem, registered oscillations in the electron density of the surrounding space. The frequency of these oscillations allowed scientists to calculate the local plasma density, and the data showed it was fluctuating. Something was actively disturbing the interstellar medium. The phenomenon repeated in April of 2013, and then again in March of 2014 and into 2015. Each time one of these waves was detected, researchers traced its origin back to the same source, our own Sunday. The cause was identified as coronal mass ejections, colossal eruptions of charged particles from the sun's surface. These powerful blasts of material travel outward through the solar system at speeds of hundreds of miles per second, their effects reaching far beyond what was once thought possible. When a powerful eruption of solar material blasts from the sun, it travels outward on an immense journey, streaming past the planets and pushing through the turbulent heliosheath, the outermost layer of our solar system. Its voyage ends only when it collides with the heliopause, the conceptual boundary where the sun's influence gives way to the galaxies. This colossal impact generates a powerful shockwave that propagates into the interstellar medium, a veritable tsunami in the vastness of the void. By the time this faint but persistent disturbance finally reaches the Voyager 1 spacecraft, which is by then over 15 billion miles away from the event's origin, several years have passed. It represents a truly remarkable and humbling display of cause and effect playing out across cosmic scales. Our home star effectively sneezes, and years later, far beyond the boundaries of its own system, the tiny Voyager probe feels the resulting ripple. This phenomenon reveals a profound truth. The sun's influence does not simply stop at the heliopause, it actively echoes out into the wider galaxy. The heliosphere is not a sealed, placid bubble, but is better imagined as a massive drum, with the sun constantly beating on its inner surface from within. These shockwaves, once detected, became a novel and ingenious method for measuring the density of the interstellar medium itself. The specific frequency of each passing plasma wave corresponds directly to the local electron density, and as different waves washed over the spacecraft, they revealed distinctly varying densities. This proved conclusively that the interstellar medium is not uniform, showing variations of 10 to 20% over distances of just a few astronomical units. The void between the stars, it turns out, has texture, structure, and even its own form of weather. The second major surprise that awaited humanity's first emissaries into interstellar space concerned the nature of the magnetic field. Before Voyager 1 made its historic crossing, scientists had formulated a set of very clear and logical expectations based on established models. The sun's magnetic field, a product of our star's own dynamics, is shaped by its steady rotation into a vast, elegant spiral pattern. The galactic magnetic field, in stark contrast, was presumed to be oriented quite differently, as it is governed by the large-scale structure and rotation of the entire Milky Way galaxy. It stood to reason, therefore, that when Voyager finally crossed the heliopause, its magnetometers should have detected a measurable rotation in the field's orientation, a clear, unambiguous change that would serve as a definitive marker of the transition from one magnetic domain to another. And yet, in an outcome that defied all predictions, Voyager 1 detected essentially no rotation whatsoever. The direction of the magnetic field on the interstellar side of the boundary was found to be almost perfectly indistinguishable from its direction on the heliospheric side. This result was profoundly baffling to the scientific community, creating a deep and persistent puzzle that lasted for over a year. It led some skeptical scientists to argue that perhaps Voyager 1 had not actually crossed the heliopause at all, but had instead entered some unforeseen transitional region. The resolution, when it finally came, was at once both mundane and profound. It was an extraordinary coincidence. The local interstellar magnetic field, at the precise point in space and time where Voyager 1 made its crossing, just so happened to be running roughly parallel to the sun's own field. Two completely independent magnetic systems, generated by entirely different physical processes on vastly different scales, happened to align in the one specific spot where humanity had managed to place a magnetometer. The subsequent crossing of Voyager 2 inches 2018 provided the crucial evidence that confirmed this interpretation. At its own crossing point, located roughly 119 astronomical units from the Sun, but in a completely different direction from its sibling probe, it detected a distinct rotation of about 20 degrees. A different location in space yielded a different field orientation, just as the original models would have suggested. This second data point proved that the galactic magnetic field is not a uniform sheet. On the contrary, it varies significantly over scales of just 100 astronomical units. The established models that had treated the local interstellar field as a smooth, predictable, and monolithic structure were revealed to be far too simple. The third surprise involved the universe's most energetic travelers, cosmic rays. These particles are atomic nuclei, stripped bare of their electrons and accelerated to nearly the speed of light by unimaginably violent phenomena such as distant supernovae. Scientists fully expected that once Voyager crossed the heliopause and finally exited the heliosphere's protective magnetic shield, it would find itself bathed in a roughly uniform flux of these cosmic rays, arriving from all directions across the sky. But the measured flux was anything but uniform. Instead, a clear and undeniable asymmetry emerged from the data, with significantly fewer cosmic rays arriving from the direction of the galactic center. This finding was deeply counterintuitive. The galactic center is the most active region of our galaxy and hosts the majority of its supernovae, so it should logically be the brightest and most powerful source of these particles. It appears, however, that the galactic magnetic field is also substantially stronger toward the center, effectively trapping and scattering these energetic particles long before they can reach our local solar neighborhood. The cosmic ray sky, as seen for the first time from interstellar space, is not evenly lit. It possesses bright and dim regions, its geography shaped by the invisible architecture of the Milky Way's magnetic field. Both probes also confirmed another measurement, one with direct and serious practical implications for our future. The intensity of cosmic rays in interstellar space is a full 10 to 20% higher than it is just inside the heliosheath. The heliosphere, our solar system's protective bubble, provides measurable and vital shielding from this radiation, even at its most distant and tenuous edge. This is critical information for the future of human space exploration. Any mission that aims to travel beyond the heliosphere must be designed to account for this significantly increased radiation environment. Furthermore, our assessments of potential habitability on planets around other stars must now consider whether those parent stars provide a similar degree of shielding for their own planetary systems. Taken together, these groundbreaking discoveries painted a picture of interstellar space that was far more complex and dynamic than anyone had previously imagined. It is not an empty, quiet, or featureless expanse. It is a structured, magnetically complex, and constantly shifting environment where the echoes of distant stars ripple outward, where magnetic fields twist and vary on surprisingly small scales, and where the flow of energetic particles is channeled and sculpted by powerful, invisible forces. The space between the stars is not nothing. It is emphatically something, a tangible, physical medium that we are only just beginning to understand. It is a place we have only just begun to measure, and a place that, as we will learn, occasionally reaches in to touch our own planet in ways that may have profoundly altered the course of life on Earth. Voyager gave us our first direct taste of this exotic environment, 2 solitary data points in an endless ocean of unknowns, 2 tiny thermometers dipped into an atmosphere that stretches across the entire galaxy. The readings they sent back were merely the opening sentence of a story that will likely take centuries to fully tell. But even those first few words were powerful enough to overturn decades of scientific assumptions. And the fundamental properties of the void itself, the density, temperature, and pressure of what was once dismissed as empty space, turned out to be among the most surprising and revealing measurements Voyager ever made. Let us now talk about nothing, not as an abstract concept, but as a physical place, the space between the stars, the interstellar medium. This is the very substance through which Voyager 1 and Voyager 2 now travel, the first human-made objects ever to directly sample the material that fills the immense gulf between our Sun and the next nearest star. To understand the nature of interstellar space, one must first face its profound emptiness. On Earth, A cubic centimeter of air at sea level holds around 25 quintillion molecules. By contrast, the same volume of space near our Sun contains an average of just 0.08 particles. This makes the interstellar medium about 10 trillion times less dense than our atmosphere. However, this incredible scarcity is not a true vacuum. These few, dispersed particles form a medium with real, measurable properties. The property of temperature presents an immediate paradox. Near the Sun, the interstellar medium registers at a staggering 54,000 to 90,000 degrees Fahrenheit, a temperature that sounds lethal. This highlights a critical distinction, however, between our intuitive sense of heat and the scientific definition of temperature. In physics, temperature measures particle speed. While the medium's sparse particles move at incredible velocities, their population is so low that their total thermal energy is negligible. There are simply too few of them to transfer significant heat. As a result, an unprotected astronaut would not be burned, but would instead freeze to death. Pressure in this environment is equally counterintuitive. Near our Sun, the interstellar medium exerts a pressure of roughly 0.00003 pascals. For comparison, Earth's atmospheric pressure at sea level is about 101,325 pascals, making interstellar pressure trillions of times weaker than a faint whisper. Nevertheless, this seemingly insignificant force is responsible for defining the boundary of our solar system. Over vast distances, the cumulative effect of these particles creates a persistent resistance strong enough to oppose the Sun's relentless solar wind. The heliosphere, the protective bubble around our solar system, forms at this exact point of equilibrium, a delicate balance between the Sun's outward push and the inward pressure of nearly nothing. The Voyager probes delivered the first direct measurements of this alien environment. Using their plasma wave subsystems, the spacecraft detected subtle oscillations in the interstellar plasma. These vibrations enabled scientists to calculate the local electron density, providing a direct gauge of the medium's substance. Critically, readings taken at various points on their journeys revealed that these density values fluctuated by 10 to 20%. This direct evidence transformed our understanding, confirming the interstellar medium is not a uniform, static void. It is instead a dynamic place with its own structure, containing regions of slightly higher and lower density, like invisible currents in a vast, tenuous ocean. Voyager also measured the magnetic field, which it found to be extraordinarily weak at about 0.5 microgauss. For perspective, the magnetic field at Earth's surface that guides a compass is around 0.5 Gauss, making the interstellar field about 1 million times feebler. Despite being almost imperceptibly faint, this field has a profound influence over galactic distances. It is strong enough to steer plasma flows, bend the paths of high-energy cosmic rays, and link star systems in an unseen web of magnetic force. This points to a fundamental cosmic principle. Like gravity, the magnetic field is individually weak, but becomes collectively dominant on the larger scales. Our Sun is currently positioned within a region known as the local interstellar cloud, a diffuse, warm expanse of partially ionized gas stretching about 30 light-years across. This cloud is itself located inside a much larger structure called the local bubble, a vast cavity in the interstellar medium measuring roughly 1,000 light-years in diameter. Scientists theorize this bubble was carved out by a series of powerful supernova explosions between 10 and 20 million years ago. Our solar system, it seems, currently resides in this relatively sheltered galactic pocket, a legacy of ancient stellar cataclysms that cleared this neighborhood long before our species evolved. This cosmic neighborhood, however, is not static. Scientific models indicate our Sun is on a course to exit the local interstellar cloud in about 1,900 years. When this happens, the solar system will enter a new region of space with entirely different properties, a new density, temperature, and magnetic field. The heliosphere will inevitably react, changing its size and shape, which will in turn affect the cosmic ray shielding it provides to Earth. This is not an unprecedented event. Evidence suggests that roughly 2 million years ago, our solar system passed through a dense interstellar cloud that significantly compressed the heliosphere. The journey is no placid cruise, but a dynamic passage through a complex, ever-changing galactic landscape. A 2025 discovery served as a powerful reminder of how much remains to be learned. Astronomers identified a previously unknown molecular cloud, named EOS, located remarkably close to us. At just 300 light-years away, this massive structure is one of the nearest of its kind ever detected. Its discovery was enabled by a novel technique using far ultraviolet fluorescence, where light from background stars made hydrogen molecules in the cloud emit a faint glow. EOS had eluded all prior surveys because it lacks the radio wave emissions typically used to map interstellar gas. In effect, this enormous structure was hiding in plain sight. The identification of EOS highlights a critical reality. Our map of the local interstellar environment is profoundly incomplete. That such a massive cloud, so close, could go undetected until 2025 forces us to ask unsettling questions. What other major structures might be lurking nearby, just beyond the reach of current detection methods? As our solar system continues its long orbit around the galactic center, what other clouds or cavities might it meet? More importantly, how might such encounters reshape our heliosphere and fundamentally change the cosmic environment surrounding Earth? For all their achievements, the Voyager probes cannot answer these grand questions. They are limited to measuring their immediate surroundings, offering just a single, tiny sample from the vast interstellar ocean. Yet that one sample has revealed an essential truth. Voyager's data has fundamentally redefined the space between stars, transforming it from a concept of nothingness into a tangible, physical place, an environment with distinct properties, complex structures, its own weather, and a deep history. It is the medium our planet is immersed in, protected only by the thin, dynamic, and imperfect shield of the heliosphere. Now that we have a glimpse of what lies beyond, the challenge changes. How do we explore more of this frontier? That question begins with confronting a piece of sobering mathematics, the math of sheer distance. Chapter 10. The Impossible Distance. The cold mathematics of interstellar travel presents a stark and sobering contrast between our collective dreams of reaching the stars and the physical reality of ever achieving that goal. Let us consider Voyager 1, which remains the fastest probe humanity has ever directed away from our Sun, moving at a sustained velocity of roughly 38,000 miles per hour. Traveling at this speed, one could theoretically traverse the entire United States in just 5 minutes, or arrive at the Moon in a mere 6 hours. Such impressive figures can create the illusion of significant progress toward the wider cosmos. But this perception, unfortunately, is profoundly and fundamentally misleading. After nearly half a century of continuous, relentless travel, Voyager 1 has covered a distance of approximately 159 astronomical units, which is about 15 billion miles. While this represents an immense journey by any conceivable terrestrial standard, it is an almost negligible distance on a true interstellar scale. Our nearest stellar neighbor, the Alpha Centauri system, lies 4.37 light-years away from us, a distance that translates to about 268,000 astronomical units. Voyager has therefore covered only a tiny fraction of that total expanse. To complete the full journey at its current velocity would require an estimated 73,000 years. a span of time that exceeds not only all of recorded history, but the entire existence of human civilization itself, from the earliest cities to the present day. It is a duration longer than the time that has elapsed since our species first began its great migration out of Africa. This single, straightforward calculation reveals the fundamental challenge. The distances involved are simply too vast for our current technology to overcome. And it is important to remember that Alpha Centauri is merely the closest star system to our own. The Milky Way galaxy itself spans an incredible distance of approximately 100,000 light-years. For a craft like Voyager, a journey across the full breadth of our home galaxy would take an almost inconceivable 1.7 billion years. Faced with such monumental timescales, interstellar travel with our current capabilities is not just difficult, it becomes a conceptually meaningless endeavor. One cannot hope to cross an entire ocean by simply stepping into the waves at the shore. Even before it could properly begin its journey to another star, Voyager must first pass through the Oort cloud, a theoretical sphere of icy bodies that is believed to encircle our solar system. The probe is not expected to reach the inner boundary of this vast region for another 300 years, and it will then take an additional 30,000 years to emerge from its outer edge. This clearly illustrates that even the act of leaving our own solar system, by its most generous gravitational definition, is a project measured in tens of thousands of years. The primary obstacle we face is not one of engineering, funding, or even political will, but rather one of fundamental physics. The sheer, unyielding emptiness between the stars imposes travel times that render our existing propulsion methods completely impractical. Yet, as Voyager's ongoing journey has clearly shown, distance is not the only problem we must confront. A more subtle and potentially more dangerous challenge emerges if we could somehow manage to build a much faster spacecraft. At Voyager's current speed, the interstellar medium, that thin distribution of gas and dust between stars, is of little to no consequence. An occasional hydrogen atom might strike the hull, but it causes no meaningful damage or measurable drag. However, in order to reach another star within a single human lifespan, a vessel would need to travel at a significant fraction of the speed of light, with 10% of light speed being a commonly cited and ambitious goal. At such extreme velocities, the very nature of the void changes entirely. A craft moving at 10% of light speed would collide with an estimated 100 trillion hydrogen atoms per second for every single square meter of its forward-facing surface. Each one of these microscopic impacts releases energy, and their cumulative effect is a constant, intense heating of the hull, amounting to thousands of watts per square meter, sustained for decades on end. Over the course of a long journey, this relentless bombardment causes severe radiation damage, makes structural materials brittle, and degrades sensitive electronic systems. The near-perfect vacuum of deep space transforms into a relentless abrasive force. Beyond this constant particle erosion, there is also the ever-present threat of cosmic rays. Data transmitted from Voyager has confirmed that the intensity of cosmic rays in true interstellar space is 10 to 20% higher than it is inside the protective magnetic bubble of our sun's heliosphere. A robotic probe could potentially be hardened against this pervasive radiation with sufficient shielding, making it a solvable, if exceptionally difficult, engineering problem. For human passengers, however, this constant exposure to high-energy radiation presents a fundamental biological barrier, raising the serious question of whether long-duration interstellar flight is even compatible with the fragility of human life. In 2016, a bold new initiative called Breakthrough Starshot was announced, aiming to leapfrog these immense and seemingly insurmountable challenges. Backed by a substantial $100 million pledge from billionaire Yuri Milner and publicly endorsed by renowned physicist Stephen Hawking and entrepreneur Mark Zuckerberg, the project proposed a radically new approach to the problem. The ambitious plan was to send a fleet of gram-scale probes to Alpha Centauri at an astonishing 20% of the speed of light. These minuscule spacecraft, each with the approximate mass of a postage stamp, would be attached to ultra-thin light sails. A massive, ground-based laser array would then focus a powerful beam on these sails, accelerating them to relativistic speeds within a matter of minutes. This ingenious concept promised to reduce the journey time to Alpha Centauri to just 20 years. A signal carrying data from the probes would then take another 4.3 years to return to Earth, meaning the entire mission could theoretically be completed within a single human generation. The idea was undeniably elegant, but the technical hurdles were staggering. At least 30 foundational challenges stood in the way of a viable mission. The light sail, for instance, it would have to withstand an acceleration equivalent to 40,000 times Earth's gravity and reflect nearly 100 gigawatts of laser power without being instantly vaporized by the tiny fraction of energy it absorbed. The tiny probe itself would somehow need to survive impacts with interstellar dust at 20% of the speed of light, a velocity where even a single grain of dust carries the kinetic energy of a fired bullet. Yet, despite all these issues, perhaps the most fatal and fundamental flaw was the problem of communication. A probe weighing only a few grams simply lacks the necessary mass, power, or antenna aperture required to transmit a detectable signal across 4.3 light-years of empty space. For a stark comparison, consider that the faintest signals from Voyager, which is currently only about 1 light-day away, require the massive 230 foot dishes of the Deep Space Network to be detected. The destination, Alpha Centauri, is more than 1,500 times farther away. The unyielding laws of physics, not just our current engineering limits, make communication from such a tiny probe over that immense distance effectively impossible with any technology we currently possess or can realistically foresee. By the year 2025, the Breakthrough Starshot initiative had largely paused its public activities. Published reports suggested that only about $4.5 million of the originally pledged $100 million had actually been spent, as the core technical problems, particularly the challenge of communication, remained without any clear or viable solution. However, the ambitious research that was spurred by the project was not without significant value. Efforts to develop advanced light sail materials, for example, continued to move forward independently. In 2025, researchers at Caltech achieved the first direct laboratory measurement of radiation pressure on a light sail. Furthermore, new and innovative materials were developed, such as tri-layer sails made of molybdenum disulfide, which demonstrated an impressive 50% reflectivity while absorbing only 4% of the incident energy, a crucial combination for surviving the intense laser launch. The individual technological components were improving, even if an integrated functional mission remained well out of reach. This, then, is the present reality of interstellar travel. We can comprehend the fundamental physics involved and are able to sketch out the necessary engineering on a conceptual level. In a sense, we know what it would take to succeed. The true challenge lies in the immense, daunting gap between our sophisticated theoretical understanding and our practical, real-world ability to build the kinds of machines that can conquer the truly incomprehensible scale of the cosmos. The immense gap between what we can currently build and what interstellar distances demand is not a challenge that cleverness alone can overcome. It requires new propulsion physics, innovative materials, novel communication paradigms, and perhaps most importantly of all, a new scale of human patience. The timeframes involved in reaching even the nearest star are measured in decades for the most optimistic concepts, and in millennia for any technology we possess today. Voyager's great contribution was in showing us what is actually out there. It revealed the environment any future mission would have to cross, meticulously measuring the cosmic rays needing to be shielded, the magnetic fields needing to be navigated, and the plasma needing to be pushed through. In doing so, Voyager drew the first crude, yet essential, map of the road between the stars, and showed us with unavoidable clarity just how incredibly long that road truly is. Yet, even knowing the distance, there are dedicated people working right now on the spacecraft that might someday follow Voyager into the void. This is not merely the stuff of science fiction. In laboratories and conference rooms, the next generation of interstellar probes is being designed, and some of them might launch within our lifetimes. The original Voyager spacecraft were, remarkably, never intended to explore interstellar space. They became accidental pioneers simply by refusing to die. The next mission will be fundamentally different. It will be conceived from the ground up with interstellar science as its core objective, and this concept is closer to reality than many might think. The Johns Hopkins Applied Physics Laboratory, the same esteemed institution that built the New Horizons spacecraft which so successfully flew past Pluto in 2015, has completed a comprehensive study for what it officially calls the interstellar probe. While daunting in its execution, the ambition is straightforward: a dedicated spacecraft designed to reach 500 to 1,000 astronomical units from the Sun within a 50-year mission. This journey would carry it 3 to 6 times farther than Voyager 1 is today, deep enough into interstellar space to map the heliosphere's nose, explore the outer Oort cloud, and potentially detect the bow shock, a hypothetical structure where the interstellar medium first deflects around our solar system's bubble. The existence and nature of the bow shock remains one of the great unsolved puzzles of our immediate cosmic neighborhood. Current models predict it should exist somewhere between 140 and 230 astronomical units from the Sun, a region where the interstellar wind first encounters the heliosphere's influence and begins to slow. This raises a question of scientific humility. Given how consistently wrong our models have been about every other heliospheric boundary, no one will be surprised if the bow shock is found in an unexpected place, has an unexpected shape, or is doing something entirely unexpected. This, perhaps, is the single most enduring lesson from Voyager, that nature is often far more imaginative than our theories. To travel 500 astronomical units in 50 years, the interstellar probe would need to achieve incredible speeds of roughly 80,000 to 160,000 miles per hour, 2 to 4 times faster than Voyager. Such a velocity is achievable with current or near-future technology. One promising approach involves solar thermal propulsion. In this scenario, a spacecraft would execute an extremely close pass of the Sun using a heat-absorbing concentrator to superheat its propellant and expel it at tremendous velocity. The physics are elegant. The closer the craft flies to the Sun, the more energy it can harvest, and the faster it can ultimately go. A solar flyby, at a distance of just 3 to 5 solar radii, skimming the outer corona, could provide the necessary boost for this epic journey. The scientific case for such a mission is exceptionally compelling. Voyager gave us 2 isolated data points on the heliopause, and the IMAP mission is mapping the boundary from within using indirect methods. But to truly understand the 3-dimensional structure of the heliosphere, its nose, its flanks, its tail, and its dynamic response to the interstellar wind, we need more direct measurements from more locations. The interstellar probe would provide exactly that, while also exploring the interstellar medium itself in far greater detail than Voyager's aging instruments can manage. It represents the next logical and necessary step in understanding our place in the galaxy. However, there is a profound and very human challenge embedded in this timeline. If the mission launches in the 2030s, its primary scientific results will not begin arriving until the 2080s. This means many of the scientists designing the mission today will not live to see its data. The project is inherently generational, a torch to be passed from one era of scientists to the next. This sobering reality raises difficult questions about institutional memory, the continuity of funding, and the fundamental willingness of a society to invest in knowledge it will not receive for half a century. The United States is no longer the only nation actively contemplating such a journey. China has proposed its own interstellar mission, sometimes called the Interstellar Express. This concept involves two separate probes, one aimed at the heliosphere's nose and the other at its tail. By measuring both ends of the structure simultaneously, the mission would provide the first comprehensive view of the heliosphere's complete shape. The publicly stated goal is to reach 100 astronomical units by 2049, the centennial of the People's Republic of China, using Jupiter gravity assists and Kuiper belt object flybys to shape its trajectory. The emerging geopolitical dimension of this new ambition is simply impossible to ignore. The exploration of interstellar space, once an endeavor solely pursued by America, is transforming into a competitive arena. It remains to be seen whether this competition will accelerate progress, as it did during the space race of the 1960s, or if it will complicate the international scientific cooperation that has become so vital. But the very fact that multiple nations are seriously studying interstellar missions suggests that the next Voyager, regardless of who builds it, is a matter of when, not if. Beyond these dedicated probes, a fascinating range of more speculative concepts are also under development. NASA's Innovative Advanced Concepts Program, known as NIAC, has funded research into swarming laser sail probes. This idea shifts the paradigm entirely. Instead of launching one large probe, we would launch hundreds or even thousands of tiny ones. Each would be a small disk about 4 meters across, made from aerographene, one of the lightest materials ever created. Carrying simple optical sensors, each disk would be accelerated by powerful lasers to roughly 20% the speed of light. This innovative swarm architecture is designed to solve one of the most serious problems facing concepts like breakthrough starshot. At 20% of light speed, collisions with interstellar dust particles are unavoidable and potentially catastrophic. A single probe has a finite chance of being destroyed during its transit, but a swarm of thousands is designed to tolerate attrition. If 10% of the probes are destroyed by dust impacts, 90% still survive to complete the mission. To further mitigate this risk, the probes would fly edge-on, presenting the thinnest possible profile to oncoming particles and minimizing their collision cross-section. Another forward-thinking concept that has been proposed involves electric sails, or e-sails. This technology is fundamentally different from a solar sail pushed by photons. An e-sail would deploy a network of long, electrically charged wires. These wires would then interact with the solar wind, the stream of ions flowing outward from the sunday. This interaction generates thrust without carrying heavy propellant, offering another potential pathway to the stars. Ultimately, it is a powerful reminder that the solutions to interstellar travel may come from harnessing the forces already present in our solar system in entirely new and ingenious ways. One proposed method uses charged wires to deflect solar wind ions, thereby generating thrust without any onboard propellant. This design, known as an e-sail, could theoretically achieve speeds of 20 to 30 astronomical units per year. Such a velocity is several times faster than that of the pioneering Voyager probes and, if successfully combined with the interstellar probe concept, could drastically reduce the travel time required to reach the outer reaches of our solar system and beyond. This raises the compelling question of just how far and how fast humanity could one day travel. Perhaps the most ambitious of all these future concepts involves transforming the sun itself into a colossal telescope. According to Albert Einstein's general theory of relativity, the immense gravity of massive objects is capable of bending the path of light. The sun, therefore, effectively acts as a powerful natural lens, focusing light from distant sources to a specific focal point approximately 550 astronomical units away. A spacecraft positioned precisely at this location could then harness the sun as a gravitational lens, achieving a magnification power millions of times greater than any instrument we could ever hope to construct on Earth. In theory, such a mission could capture direct images of an exoplanet's surface around a nearby star, resolving features like continents, oceans, and even dynamic weather patterns. While a journey to the solar gravitational lens point is within the realm of possibility for an interstellar probe, it would still require decades of dedicated travel. The scientific return, however, would be nothing short of revolutionary. The direct imaging of another world in detail currently unimaginable, a step that could finally help answer the profound question that fuels so much of this exploration. Are we alone? A common thread connects all of these forward-thinking ideas. They are fundamentally grounded in reality, not in the realm of science fiction. These are tangible engineering concepts built on established physics, each with its own identified challenges and active research programs dedicated to solving them. While it is true that none are ready for launch tomorrow, and some may never even leave the drawing board, they represent the logical next steps on the incredible path that Voyager first forged. The Voyager mission proved that a machine built on a small planet orbiting an ordinary star could successfully leave its home system and continue to function in the vastness of interstellar space. It validated the concept, drew the first map of this new territory, and took the first crucial measurements of its conditions. Everything that follows in our exploration of the cosmos will be built upon the enduring legacy of two spacecraft that were originally designed to last 5 years but are still communicating with us from beyond the heliosphere nearly half a century later. And affixed to each of these truly remarkable machines is an object with no scientific function at all. An artifact placed there not to measure the cosmos, but simply to introduce ourselves to it. This is the story of the Golden Record. During the summer of 1977, a small committee, led by the renowned astronomer Carl Sagan, was given a truly monumental task. NASA had officially approved the inclusion of a message aboard each Voyager probe, a kind of time capsule intended to represent all of humanity to any civilization that might one day discover it adrift in the cosmos. The committee was given a mere 6 weeks to complete this entire project, just 6 weeks to curate the very essence of an entire species. The medium they selected was a 1/2-inch, gold-plated copper phonograph record. This technology was already appearing dated in 1977 and would be considered a genuine antique within a decade. But this seemingly archaic choice of medium was part of its brilliance. A phonograph record is a purely physical object, one containing no delicate electronics, no complex software, no batteries, and no magnetic media that could degrade over the course of eons. Its message is physically etched into grooves on its surface. In the near-perfect vacuum of interstellar space free from air, moisture, and the biological agents that cause corrosion, those grooves are expected to last for hundreds of millions, perhaps even for billions of years. In this case, the medium itself carries a powerful message of permanence, one achieved through profound simplicity. The committee ultimately selected a total of 27 pieces of music. The selection process was agonizing, as it raised a profoundly difficult question. How can the rich musical heritage of an entire world be distilled into a mere 90 minutes of audio? The final collection included works by Johann Sebastian Bach, with the first movement of his Brandenburg Concerto No. 2, and Ludwig van Beethoven, featuring the first movement of his Fifth Symphony and the Cavatina from his string quartet No. 13. Music from Mozart and Stravinsky was also included. However, the record was intentionally designed to be far more than a monument to the Western classical tradition. It also features a Japanese gamelan performance titled Kinds of Flowers, an Aboriginal Australian song called Morning Star and Devil Bird, a piece for Peruvian panpipes and drums, a Navajo night chant, a Georgian choral work named Chakrulo, a Senegalese percussion piece, Louis Armstrong's Melody Blues, and Chuck Berry's iconic Johnny B. Good. A curious story from this selection process perfectly illustrates the intersection of cosmic ambitions and more earthly concerns. One committee member reportedly suggested including the famous Beatles song Here Comes the Sunday. However, the band's record label, EMI, is said to have refused to grant the necessary rights for its inclusion. It remains a strange footnote to the project. The music of an entire species, sent drifting through eternity, was at least partially shaped by a corporate business decision. The record also carries a collection of spoken greetings in 55 distinct human languages. This collection was carefully designed to span both time and geography. Some of the languages included are ancient, such as Akkadian, the language of the Babylonians, which has not been spoken for over 2,000 years, and Sumerian, which may be the oldest written language in all of human history. These are presented alongside major modern languages like Mandarin Chinese, English, Russian, Hindi, and Arabic. A few greetings add a deeply personal touch, including one in the constructed language of Esperanto, and a simple, heartfelt message from a child, who says in English, "Hello from the children of planet Earth." A total of 116 images were also encoded onto the record, having been translated into audio waveforms. The record's protective cover provides detailed instructions on how to decode these signals back into pictures. The images offer a broad visual summary of our world, including a diagram of the solar system, fundamental mathematical definitions, the structure of DNA, and various illustrations of human anatomy. They also contain photographs of people engaged in everyday life, eating, drinking, teaching, and building, as well as a moving image of a woman nursing an infant. A page of sheet music from a Beethoven string quartet, the very same cavatina heard elsewhere on the record, is included, alongside photographs of Earth's diverse landscapes, a sand dune, a lush forest, and a sunset over the ocean. One particular photograph of a supermarket now looks almost as dated as the phonograph technology itself, serving as a reminder of how quickly our world changes. The diverse sounds of our planet were gathered and carefully curated by science writer and musician Timothy Ferris, who served as the record's official producer. This auditory collection includes a baby's first cry, a mother tenderly kissing her child, and the elemental sounds of rain, wind, surf, and thunder. It features birds singing and the long, eerie, and complex vocalizations of humpback whales, which are songs we still do not fully comprehend. The soundscape also captures a dog barking, the powerful rumble of a Saturn V rocket engine, the distinct rhythmic pattern of Morse code, and the steady pulses of a pulsar. The cover of the record was ingeniously designed to function as a kind of Rosetta Stone for any potential finders. Etched into the protective aluminum jacket is a set of diagrams that explain exactly how to play the record, including the correct rotational speed and the proper way to position the included stylus. These instructions also show how to decode the images from the audio signals. To ensure the message is as universal as possible, the diagrams use binary notation based on the fundamental transition of the hydrogen atom, the most common element in the universe. The cover of the Golden Record features a unique map designed as a guide for any potential finders. Its lines point toward 14 specific pulsars, which are rapidly spinning neutron stars that serve as reliable celestial landmarks. The length of each individual line encodes the unique radio frequency of that particular pulsar. Because these frequencies change in a predictable way over time, the map serves a dual purpose. It not only pinpoints our sun's location within the galaxy, but also provides a timestamp for the record's creation. While the cover's clever engineering is a statement on human ingenuity, the record's actual content speaks to our deeper values. What is most telling, perhaps, is what was intentionally and thoughtfully omitted. There are no images of war, no weapons, and no suffering. The committee deliberately excluded political ideologies, national borders, and any form of propaganda, choosing instead to present a truly aspirational portrait of humanity. This decision raises a profound question about how a species chooses to represent itself to the universe. The record is not a documentary in the traditional sense, but rather an idealized vision, a message that seeks to be remembered for its music, its curiosity, and its capacity for wonder. As Carl Sagan himself noted, the record would only ever be played if it were found by an advanced, spacefaring civilization. Yet the very act of launching this bottle into the cosmic ocean was in itself a profound statement of hope. The statistical reality of the situation, however, is stark. The probability of its discovery is virtually zero. The Voyager probes are not aimed at any particular star, but are instead drifting aimlessly through the galaxy on trajectories that were set by planetary encounters decades ago. In about 40,000 years, Voyager 1 will pass within 1.6 light-years of the star Gliese 445, but at a distance of over 9 trillion miles. This is by no means a close encounter. The spacecraft will not be captured into orbit. It will simply glide past at 38,000 miles per hour, a cold and entirely invisible artifact. The estimated timescale for a random collision with any star is roughly 10 to the 20th power years, a duration that is more than 1 billion times longer than the current age of the universe itself. Given these astronomical odds, it is almost certain that no one besides us will ever play the golden record. But its discovery was never the true objective of the project. The project's ultimate value was not in its potential reception, but in the very act of its creation. It was a rare and significant moment when our species, then embroiled in a cold war on a planet beset by conflict, paused for a period of collective self-reflection. The process forced the committee to ask a series of critical questions. What is truly beautiful about humanity? What aspects of our existence are worth preserving and sharing with the cosmos? And what, fundamentally, would we want an unknown intelligence to understand about who we were? The record, therefore, serves as a time capsule, not just for potential aliens, but perhaps more importantly, for humanity itself. Some of the languages included in its greetings are now extinct. The musical traditions it captured have evolved, and many of the people whose voices are recorded on it have since passed away. It is a perfect snapshot of Earth, as it was in 1977, a frozen moment drifting through eternity while the planet that made it continues to change. One day, that world will inevitably fall silent. This artifact, however, is built to endure. The golden record will outlast the pyramids and the continents, possibly even outlasting the sun, making it the most durable object our species has ever created. And etched deep into its grooves is the simple, universal sound of a mother kissing her child. A new chapter for the Voyager mission began on February 14th, 1990. The spacecraft was already 3.7 billion miles from home, its primary planetary mission having been complete for a decade. Its cameras were turned off to conserve precious power, as there was seemingly nothing left to photograph in the void. But Carl Sagan had been lobbying NASA for years to turn them back on, not for a planet or a moon, but for one last, final picture of home. NASA initially resisted the idea. The image would have absolutely no scientific value, and the aging cameras risked permanent damage by pointing them so near the sun. At that immense distance, Earth would be smaller than a single pixel. What, they reasonably wondered, was the point? Sagan's persistence ultimately paid off. On Valentine's Day, 1990, NASA finally relented. Voyager 1 rotated its scan platform, aimed its narrow-angle camera back toward the inner solar system, and took a total of 60 frames, creating a family portrait of our cosmic neighborhood. 6 planets were successfully captured: Venus, Earth, Jupiter, Saturn, Uranus, and Neptune. Mars and Mercury were too close to the Sun to be imaged, and Pluto was simply too small and distant. In one particular frame, Earth appeared. It was a tiny point of light, a mere speck suspended in a beam of scattered sunlight. an artifact of the camera optics that just happened to frame our world. It was, and is, a pale blue dot. Looking at that photograph, Carl Sagan wrote what has since become one of the most quoted passages in the history of science communication. He urged us to look again at that dot, explaining that it is here, it is home, it is us. On it, he reflected, everyone you love, everyone you know, and every single human being who ever was, lived out their lives. Every hero and coward, every creator and destroyer of civilization, every king and peasant, every saint and sinner in the entire history of our species lived there on a mote of dust suspended in a sunbeam. The photograph itself has no scientific content. Nothing can be learned about the planet Earth from it. You cannot resolve continents, oceans, or cities. It is, in the end, just a dot. And yet, it is perhaps the single most important photograph ever taken. Its power is not found in data but in perspective. It does something that no other image has ever done. It shows us our planet as the universe itself sees it, tiny, fragile, and utterly alone. This single pixel forces a profound and necessary re-evaluation of our place in the cosmos. The spacecraft that took that photograph kept going, continuing its journey outward. 22 years later, it finally crossed the heliopause into true interstellar space. From that incredible vantage point, Earth is not just small. Our entire solar system is but a tiny bubble adrift in the incomprehensible expanse of the Milky Way galaxy. The journey of Voyager thus offers us a final, humbling lesson in cosmic scale. In the vast expanse of the Milky Way, our Sun is just one of an estimated 200 billion stars. Our entire solar system is enveloped by the heliosphere, a protective bubble of space within a galaxy that stretches 100,000 light-years from edge to edge. From the vantage point of interstellar space, Earth would be completely invisible. Even our Sun would appear as just another faint point of light, lost in a sea of billions. The Voyager mission has given us something profoundly rare: perspective. This is not the perspective gained from climbing a mountain or looking out an airplane window. It is the kind that comes from leaving everything you have ever known behind, only to look back and see it all shrink to a single fragile point. To truly grasp this, one must consider the scales of time and space. Our planet is 4.5 billion years old, while Homo sapiens have existed for only 300,000 years. Civilization, defined by organized societies with agriculture, is just 10,000 years old, and the space age began less than 70 years ago. The Voyager missions have been traveling for 49 of those years. Yet in all that time, moving at a staggering 38,000 miles per hour, they have barely crossed the threshold of our cosmic home. The Oort cloud, marking the outer gravitational boundary of the solar system, extends to roughly 100,000 astronomical units. Voyager 1, currently at 159 astronomical units, has traveled less than 0.2% of the way to that outer edge. These figures raise a fundamental question about our place in the cosmos. Are our greatest achievements truly significant on a galactic scale? The probe's silent journey into the void is a testament to both human ambition and the sheer emptiness of interstellar space. It will take another 300 years for Voyager 1 to reach the inner edge of the Oort cloud, and a full 30,000 years to pass through its outer boundary. Even then, the nearest star remains incredibly distant. In roughly 40,000 years, the spacecraft will make its closest approach to another star, a dim red dwarf named Gliese, 445 inches, the constellation Camelopardalis. Yet this close encounter will still see Voyager passing at a distance of 1.6 light-years, or over 9 trillion miles away. It will not be close enough for gravity to capture it, nor for anything more than a fleeting cosmic near-miss. The spacecraft will simply drift past, cold, dark, and silent, its dead instruments and golden record carried through a void so vast that 40,000 years of travel barely makes an impression. This vast expanse of time forces us to confront an unsettling possibility. Will the civilization that launched Voyager still exist to remember it? Will anyone be left to recall these voyages, or listen for a signal that ceased transmitting sometime in the early 2030s? 40,000 years ago, our ancestors painted animals on cave walls in Europe, crafted tools from stone, and buried their dead with flowers and ochre. They had no cities, no writing, no agriculture, and no technology beyond fire and sharpened rock. The gulf between their world and ours is the same immense temporal distance that separates us from whatever future Voyager will witness. And that distance contains every possibility, including the profound silence of our own absence. The famed pale blue dot photograph acts as a mirror. It doesn't show us something new about the universe. It shows us something new about ourselves. It reveals that every border we draw, every conflict we wage, and every grievance that consumes us plays out on a mote of dust suspended in a sunbeam. It demonstrates that every empire that ever rose and fell did so on a world so small that, from a great enough distance, it vanishes completely. This realization is not a cause for despair, but rather a powerful argument for care. The pale blue dot is all we have. There is no backup plan, no escape route available. If we destroy this world, we have destroyed the only one we can ever reach. The Voyager probes, drifting through the void with their messages of music, mathematics, and the sound of a baby's cry, remind us of what we are capable of. They represent our ability to achieve extraordinary things, to reach beyond ourselves, and to speak across distances that mock every human conception of far. The cameras on Voyager 1 were turned off decades ago. It can never take another photograph or look back at us again. But the image it left behind continues to speak, quietly and persistently, from a distance that grows larger with every passing second. Somewhere, right now, a signal is reaching a 230-foot radio dish in the Australian outback. It has travelled for nearly 24 hours at the speed of light, crossing 15.7 billion miles of empty space. The signal itself is impossibly faint, measuring roughly 1/10 of a billion trillionth of a watt. It is the weakest whisper human technology can possibly detect, and it originates from Voyager 1. This faint transmission carries data at just 160 bits per second, slower than the earliest dial-up modems. But each bit is precious, as it comes from the only instruments humanity has ever operated in interstellar space. With these few remaining senses, humanity continues to probe the environment beyond our solar bubble. The data comes from a magnetometer measuring the galactic magnetic field, a plasma wave detector listening to the vibrations of interstellar gas, and a low-energy charged particle instrument counting the cosmic rays that stream through the void. As of 2026, these three instruments are all that remain active on Voyager 1, out of an original suite of 10. Its twin, Voyager 2, also has 3 still in operation. This managed decline is a race against time, a careful rationing of dwindling power to ask a few final questions. One by one, over the last several years, the other instruments have been switched off. The cosmic ray subsystem on Voyager 1 went dark in February 2025, and the low-energy charged particle instrument on Voyager 2 was shut down the following month. The plasma science instruments on both spacecraft were turned off even earlier. Each shutdown was a small death, a sensor going blind, a question that can no longer be asked. In 2026, another round of shutdowns is planned, which will leave each spacecraft with just 2 instruments, the magnetometer and the plasma wave subsystem, 2 final tools to measure the void. The laws of physics, not human choice, will ultimately dictate the end of this historic mission. The power budget tells the rest of the story. Each spacecraft's plutonium power source decays at a fixed rate, causing a loss of about 4 watts of power per year. By 2030, perhaps as late as 2032, there will be insufficient energy to run even a single instrument and the transmitter at the same time. At that point, the engineering team will face its final decision: when to send the last command and let the spacecraft go. The transmitter will fall silent. The last signal will race toward Earth, arriving 24 hours later at a receiving dish. Engineers will log the final data point, and then there will be nothing. No more signals will arrive from interstellar space until another spacecraft is built, launched, and travels for decades to reach the heliopause. The window that Voyager opened will close, possibly for an entire generation, but the spacecraft themselves will not stop. In the frictionless vacuum of interstellar space, there is no air resistance, no drag, nothing to slow them down. Though we will no longer hear from them, their physical journey has only just begun. Voyager 1 will continue traveling onward at 38,000 miles per hour, a silent emissary on an eternal voyage. The two Voyager spacecraft are now embarked on a journey that will last effectively forever. Decade after decade, millennium after millennium, they will drift silently through the interstellar medium they were the first to explore. Though their instruments are cold and their computers have fallen silent, the probes themselves are built to last. Their gold-plated structures will not corrode in the vacuum of space, and their metallic parts will never rust. The golden records affixed to their sides will carry their grooves into eternity. This timeless voyage has a distant itinerary. In approximately 300 years, Voyager 1 will arrive at the inner boundary of the Oort cloud, beginning a passage that will take 30,000 years to complete. While trillions of icy bodies orbit in this distant realm, the space between them is so vast that an encounter is exceptionally unlikely. Farther still, in about 40,000 years, the probe will have its closest encounter with another star, passing within 1.6 light-years of Gliese 445, a cosmic near-miss, not nearly close enough to be captured by the star's gravity. On a timescale of millions of years, the cumulative gravitational influence of distant stars will gently reshape the paths of both Voyager probes. Their trajectories will curve and shift under these subtle, persistent forces, eventually placing them into a grand orbit around the center of the Milky Way. Each revolution, a single galactic year, takes about 225 million years. They will circle the galaxy not just once, but many times, carrying the sounds of Bach, Beethoven, and Chuck Berry through spiral arms, past glowing nebulae and the remnants of ancient supernovae. The sheer emptiness of space ensures their survival. The estimated time for a random collision with a star is on the order of 10 to the 20th power years, a duration so immense that the current 4 billion year, all age of the universe is insignificant by comparison. Barring an unlikely disruption, the probes will remain fundamentally intact for a span of time that defies human comprehension, becoming a testament to endurance on a cosmic scale. The scientific legacy of the Voyager missions is defined by a series of major discoveries that consistently overturned our predictions. At the edge of the solar system, the termination shock was found at 94 astronomical units, farther than the expected 75 to 90. The heliopause, the true boundary with interstellar space, was located at 121 AU, again beyond the predicted 90 to 100. Even the shape of the heliosphere itself was a surprise, resembling not a comet but a deflated croissant. Beyond our sun's influence, the probes revealed a universe far more intricate than anticipated, a magnetic highway connecting our system to interstellar space, a surprisingly variable galactic magnetic field, and an interstellar medium that was dynamic and textured, not uniform. Finally, they found that cosmic rays were distributed unevenly, sculpted by a galactic magnetic architecture we are only just beginning to map. The fact that every one of these predictions was incorrect is not an indictment of the scientists who made them. Instead, it serves as a powerful reminder that reality is always more complex and nuanced than our models can capture. What these findings reveal is a consistent pattern. The universe rarely simplifies itself for our convenience. This underscores a fundamental truth of exploration. The only way to truly know what lies in the void is to venture into it and observe directly. But perhaps Voyager's most profound legacy is not the wealth of data it collected, nor the golden record it carries as a cultural time capsule. Its greatest contribution may be the simple proof of concept. It demonstrated that a species on a small, rocky planet could construct machines from metal, silicon, and plutonium, launch them into the cosmos, and have them continue to function and communicate nearly half a century later. Voyager proved that interstellar exploration, while primitive and slow, is possible. This achievement marks the first step on a path that stretches beyond our current imagination, a path that began with technology we now consider rudimentary. Probes built with less computing power than a pocket calculator, transmitting with less power than a light bulb. Even now, a signal from that distant frontier is crossing the void, carrying the sound of a human heartbeat on a phonograph record into the space between the stars. At just 160 bits per second, it is a faint whisper from the edge of everything. That whisper grows fainter each year, but it is still there, still speaking. If this documentary was meaningful to you, we invite you to like the video and subscribe to Calm Space. Your support allows us to pursue more investigations like this one. The mission compels us all to ask what we have learned and what we should explore next. These are not inquiries reserved for scientists. They are questions for all of humanity. The edge of the solar system represents more than just the limit of the sun's physical influence. It marks the boundary of everything we have ever known. What lies beyond that frontier is the next chapter in the unfolding story of who we are.